and second critical angles. So we just did Snell's law, and now we're going to do first and second critical angles, meaning, using the Snell's law formula, if we are looking for a first critical angle, we're looking for where the longitudinal wave has been reflected out, or at least refracted to 90 degrees, right? Alright, so we're still going to use Snell's law formula, and then we keep tipping this transducer back farther and farther, and the second critical angle is the same thing, meaning when the wave gets refracted out to 90 degrees, or reflected out, but it is the shear wave. So it's when the shear wave gets reflected out, or refracted back to 90 degrees, creating a surface wave, right?
Yes.
Alright, so let's grab a couple of numbers here. First and second critical angles. You guys get your sheets open there, first and second critical angles. Okay, we need to know the first and second critical angle between what? Water and steel?
Water and steel.
Alright, so water and steel. I'm just going to write, whoops, H2O, steel. So, we already have three pieces of the puzzle like we already did before, except this time we need to know what this angle is. Meaning, we don't know the sine of angle 1 because we know, or that we know, I should say, we already know. Sound correct here. Write the right number. We know that the longitudinal wave is going to be refracted out or reflected out to 90 degrees. Right? So, here's our sine of angle 1. We don't know what that is, but we already know that this is 90 degrees over here. Okay? Compressional velocity, 58,400, correct? Right off your sheet, inches per second. Compressional velocity of steel, 230,000, right?
You want the compressional in this and not the shear?
We only want compressional first because we want to know where the longitudinal velocity, or sorry, where the longitudinal wave is refracted out. Okay? So, work this on your calculator. I got my calculator here, so I can make sure I'm following the correct numbers. The sine of 90 degrees, that's how much?
1.
1, right? So cross multiply, sine of 90 times 58,400 should come out with 58,400, right?
Yes.
Okay, so 1, sine of 90 times 58,400, cross multiply and divide by 230,000.
0.25391.
0.25391 if we stretch it out a little ways. Let me get my marker ready here. So all that worked out is 0.25391. And that equals the sine of angle 1.
So that's the answer?
You know, that's the answer to give us the to give us the sine, but we need the actual angle. Okay? So just like Snell's law, just like we did, we're still going to do inverse sine of this. Okay? Inverse sine of this number. So inverse sine, here we go, of 0.25391 equals roughly
14.709.
14.709, and it stretches on out.
My decimal's probably off.
What's that?
So. Is my decimal not off?
Nope, you're right.
Okay.
So if you inverse sine this number, you come up with 14.709. Good with that?
That's your first critical angle.
That's the first critical angle, meaning this degree here, 14.709, roughly 15 degrees, okay? Roughly 15. That's where the longitudinal wave is refracted out, or at least to 90 degrees, right? Good with that, Nick? So let's get rid of those, and let's go second critical angle. Just like Snell's law, we only can create compressional wave modes to start with. So
That was the first critical angle.
that was the first critical angle. This one's going to be the second critical angle.
Okay.
So just like we did before, we can only create compressional wave modes in water. Okay, so we know we're still going to have a compressional velocity for material 1. That's just what has to happen. Okay? So compressional velocity here. Now we need the shear velocity for steel.
130,000.
So 130,000. I'm going to write this over here just for notes. First critical angle is 14.709. Okay, sine of 90 again is 1, right? So 1 times 58,400 is itself. So 58,400 divided by 130,000 equals what I have .449, right? And then it stretches on.
Yes.
I've got .449230769. Good with that? So I'm just going to stretch it out to 3 here. Now I need inverse sine of .449.
26.69434.
That's plenty.
What number are you getting, Jay?
That was number 1. 26.69 degrees for the second critical angle.
That water still.
Yep. Good with those? That tells us this. If we started out normal to the surface, we tip this back, we're in water at 14.71 roughly. We're going to reflect the longitudinal wave out. We're going to be left with shear. Keep tipping that back to 26, roughly 27, and we're going to refract out or reflect out the shear wave. Right? Good with all that? Wonderful.
So what, they got a different formula?
Yeah, I'm glad I came to class today.
That's good.